This is college algebra, exponential functions.
Here we're still in section 3.1. This is the third part of the section, and the main focus of this part of the section will be applications of exponential functions. And the first application we're going to look at is interest. So we have this definition here. It says compound interest. If P dollars, that stands for principal, that is the amount of money, principal dollars, are deposited into an account earning interest at an annual rate. So this is a good analogy would be a credit card interest. It's an annual rate of 14.99% or something along those lines. At an annual rate, compounded K times a year, semi-annually, quarterly, anything like that, monthly, compounded a certain number of times a year, we end up with these two formulas right here. Now, this formula is what we're going to look at right now. Let's break it down once again. P stands for principal. And principal is the amount of money that you invest initially. R is the rate that you're getting paid to invest your money, or the rate that you're paying back the money you borrowed. K is how often it is compounded. Number of times compounded per year. And that's interesting. That's important. It's per year. Don't forget that. And then up here we have this KT, excuse me, where we have the same K. K is still the number of times it's compounded per year, but T represents the time that we're looking at. So we might have a monthly compounding schedule, but we only want to know how much money is going to be in the account after, I have no idea, after 5 months. So K would be monthly, that's 12 times a year, K would be 12, and then the time would be 5 months. So up here at the top, we would have an exponent of 60, because 12 times 5 will give me that 60 there. So this formula has a lot of variables in it, I know that. It has a whole lot of variables in it, but it focuses primarily on just some common aspects of interest that hopefully you've seen before, the idea of principal, rate, and time. So we have this first example where it says, suppose that you are putting $12,000 into a savings account, and it has an annual interest rate of 2.5%. Now, we want to calculate the amount of money in the account at the end of the 6th year. Now, let's take a look at it. The interest is compounded monthly. It's the first option we're given. So if it's compounded monthly, then K is going to equal 12. And then we have the interest is compounded daily. That would be K equals 365. Because remember, K is the number of times compounded per year. So 12 months per year, right here. And this one down here is 365 days per year. So the K value is going to help us figure out this interest, but we have to remember that it's always per year. So as we continue on in this problem, let's do the mathematics here now. I'll just set it up. We'll talk about calculator issues in just a minute. On this one, where the interest is compounded monthly, we have a principal of $12,000. We have a rate of 2.5%. More about that in a second. And as we've already discussed, K is 12 times a year. And then our T, our time, is 6 years. Now, what I was going to say about rate is right here. Remember, we cannot use a percentage in mathematical formulas. We always convert our percentage into a decimal number. So 2.5% is the same thing as 0.025. And if you remember, we have 2 or 3 ways of converting from percent to decimals and vice versa. But the most practical way, I suppose, would be either to divide your percent by 100, because 2.5 divided by 100 is 0.025, or to use the time-tested practice of move your decimal 2 places to the left and get that decimal conversion. However you do it, when we do this problem here, let me erase out this. When we do this problem, we are going to just plug in these four things into our formula. A equals the principal times 1 plus r over k to the kt. We're just going to plug these things in, and we're going to find out how much money we have at the end of 6 years. So the amount equals our principal of $12,000 times 1 plus our rate of 0.025 over k, the number of times compounded per year, to the 12 times 6 up here on the top. All right, so that's the formula to go with this guy. Now, the only difference between the formula with compounded monthly and compounded daily is k value, right there. So for the second part, where it's compounded daily, we're going to have the amount equals the principal times 1 plus rk over k to the kt, which is going to give us 12,000, once again, times 1 plus 0.025 over 365. Remember, that's the only thing that changes, to the 365 times 6. So these two formulas, let me put this one in a box. This one is compounded daily, as we said, 365. And this one over here, that I'm kind of writing around, this one is compounded monthly. So the formulas are very similar, except for that k value. So we got that idea that k value is extremely important here. Now, the calculator issues. The calculator